Hi, my name is Alex Rockwell, and today I'm going to take you through my Module 5 Practices response. So for my Rich STEM activity, I actually chose an activity that I talked about in my intro video that I already do with my 4th grade math and science students, but I have updated it a little bit and used some of the things that we've talked about to make it more of a multidisciplinary approach. So the activity is a hovercraft challenge, and the question that the students have to answer and have to design is, how do you design a hovercraft and how can air be used to reduce friction? So this comes after our force and motion unit where we talk about friction, and the students are going to get all of these different materials here. I mean, there's different size paper plates, CDs, cardboard, book tape, duct tape, different types of glue, and different types of balloon attachments, so pop tops or wooden spools, and they have to use those to design a hovercraft that will most effectively reduce friction and travel the greatest distance. And then we make it a little bit of a challenge to motivate the students. So the first step is to research. So here I have some pictures of my students doing a little bit of research on how they're going to make their hovercraft. Next, after they research and they design a hovercraft, they actually go through and create it. As you can see, I've got a couple different materials being used here. A lot of people choose the plastic red plate. This is like a sports bottle cap. Here's a CD. You can't really tell, but that's a wooden spool there. We've got duct tape over here, some Elmer's glue, some Gorilla Glue, so just all different combinations that the students design with their teams that they think will reduce the most friction. So after they create their hovercraft, they have to measure and weigh it, and this right here actually comes right from their packet that they have to fill out. So they have to measure the mass, so they have to weigh it. You can see here he's weighing it on that scale, and then measure the width. That way, when they do their first test, if they need to go back and improve, they can tell, okay, we need to make it heavier or we need to make it lighter. Now they have that concrete data so that they know if they have successfully improved it. Then they do their first test. They do their first test on their own, so there's no, I don't help them pump up the balloon or push the hovercraft or anything like that. So we've got a couple of them here blowing up the balloon. Here's some they're measuring the distance, how far it went. And then after they test it, they obviously can go back and improve what they have already made to do a final test. So I have a video here of students testing their own. There we go. So you can see how it hovers, and that would be a great one, but then they might go back and decide how can they make it go further, how can they make it not veer off to the side like that one did. Then I'm going to add in this year a little bit more of a math connection where they have to obviously write down their distances. We are going to do it with and without the balloon to really discuss the amount of friction and if they are reducing friction. Then they have to compare those distances and then compare the distances between the first and second trial with the balloon. So that brings in some subtraction there, and it could be subtraction of fractions as well, depending on how in-depth we go with our measurements, how specific we are. And then lastly, adding their distance to the class bar graph. So then we can talk about graphing, how to use graphing to collect data on how to analyze that graph to see, did a certain material work the best? And there's lots of different conversations that we can have. So these are just some of the groups with their final hovercrafts. But thank you for listening, and the rest of my analysis is in the post. Thanks.